The second talk I am preponing.
Oh, okay. Yeah. So
good afternoon, sir. Somesh, sir. Good afternoon.
Good afternoon.
Yeah, so it has been started. YouTube streaming has been started.
Yeah, YouTube is live.
Yeah.
Hi, sir. It's coming. Okay, sir. Can we start? Somesh, sir. Can we start, sir?
Yeah, you can start.
Okay. Good afternoon, all. Welcome to the weekly online lecture series of on radar meteorology, organized by South Asian Meteorological Association and Advanced Center for Atmospheric Radar Research, Cochin University of Science and Technology. This is the lecture number 11. Today, the lecture will be conducted by Dr. T.N. Rao, scientist NARL Gadangi, on the topic wind profiler for meteorological applications. So, before the start of the topic, we will start the proceedings. I welcome Professor Someshwar Das sir for the initial address.
Thank you very much, Mr. Rakesh. Good afternoon, everybody. ABM, Professor Tyagi sir, President of SAMA, today's speaker, Dr. T.N. Rao, and he's also the member of the advisory panel of our lecture series. Dr. Devendra Pradhan is the chairman of the advisory panel of this lecture series. Our organizing committee members, Dr. Swagata, Dr. Lakshmi Kumar, Dr. Mili, and also our representative from Bangladesh, Mr. Shah Alam. Good afternoon, everybody, and welcome on behalf of the South Asian Meteorological Association and ACARR, the Advanced Center for Atmospheric Radar Research at Cochin University of Science and Technology, India. As already been said, this is the 11th lecture. Last week we could not have the lecture because of the Foundation Day celebration of SAMA. So the lecture which was scheduled last week has been postponed. And we shall let you know about the date of the lecture as per the convenience of the speaker later on. This is the first lecture of Dr. T.N. Rao Sahab. So I like to say a little bit background of this lecture series, which has already been told earlier. So all the participants are already aware of it. So this is the fourth lecture series being conducted by SAMA, Radar Meteorology. The first one was on atmospheric physics, which was conducted for 4 months in collaboration with the SRM Institute of Science and Technology at Chennai. The second one was lecture series or training on WRF modeling system, which was conducted in collaboration with the CDAC, which is the Center for Development of Advanced Computing in India. The third one was the lecture series on satellite meteorology, which was conducted for 20 weeks. That was conducted in collaboration with the Birla Institute of Technology at Mesra. And this is the fourth one, which is being organized in collaboration with ACARR at CUSAT. As you already know that we have a distinguished panel of very senior scientists and professors from reputed institutions of this region who are experts in the field. The syllabus of the lecture series has been designed based on the feedback of the participants and requirements of the member countries, basically, some of member countries. The lecture series is targeted to postgraduate students and professionals of non-meteorological background who are interested in learning the subject of radar meteorology. This lecture series will continue for about 20 or 22 weeks. As of now, already more than, I think, roughly 1,200 people have registered for this course from about 48 countries. That means countries which are outside the South Asia have also registered for this course. As has already been announced, certificates will be given to the participants who can at least 75% of the lectures. Can you switch off your mic, Dr. Madan Sikdin? So those interested in receiving certificates with grades like outstanding, excellent, etc., they will have to attempt an evaluation test which will be conducted at the end of the lecture series. All the lectures, as you know, are streamlined on YouTube, and the past lectures are available on the YouTube channel of SAMA. So those who missed some of the lectures, or those who cannot attend the lectures online because of the time difference between India and other countries, they can always watch the lecture on the YouTube channel of SAMA. We shall have interaction session between the speaker and the participants of the lecture series at the end of the lecture. So please write your questions in the chat box, and our moderators will pick up the questions at the end of the lecture, and they will be answered by the speaker. So enjoy the lectures and have a good day. So over to you, Mr. Rakesh.
Thank you, sir, for the address. Now I welcome AVM retired Professor Ajit Tyagi, sir, President of SAMA, for the presidential address.
Yeah. Thank you, Rakesh, and a welcome address by me is a formality, but it's not formality in the present case that we have a Dr. T. Narayan Rao, a scientist G and senior scientist at the NARL. NARL is a premier institution where when we talk about radar from boundary layer to the stratospheric, monitoring wind profilers are there. So entire spectrum of radar technology is being used both for research and also for capacity building in the country. So we are really happy to have Dr. Narayan Rao. He has been, in fact, our family member, being part of our scientific advisory committee, and also been supporting various activities of South Asian Meteorological Association. He is a well-known figure in the field of radar technology and meteorology applications, and he's been duly recognized as a fellowship of our premier institutions like INSA and the Indian Academy of Sciences. Also, ISRO team award also conferred on him. Besides this, he has been guiding, the biggest satisfaction for any scientist is to mentor a number of students. So he has guided more than 13 students for their PhD. So this is a great capacity building support provided by Dr. Narayan Rao. Thank you so much. This also is an attempt by SAMA to spread the knowledge about radar meteorology to the many people who don't have access to the premier institutions like NARL or the academic institutions in many of the countries in the region. So idea of doing these online lecture series is to enable these interested students and the professionals who benefit by the experience of eminent scientists like Dr. Narayan Rao. So thank you so much. I know that this is on the short notice. You have agreed to our request to deliver this lecture. So thank you so much. And Wind Profiler is a powerful tool. In fact, it always fascinated me to when something from there, the studies were done of various higher levels of the upper troposphere, stratosphere, and it was being termed as one of the premier instrument in the developing countries. So it's a very important part of our scientific studies. Thank you so much, Dr. Narayan Rao, and I'm sure your presentation will benefit all our students. And we do have, as Professor Somesh has brought out, these are available on the YouTube also, so that some of these students, because of time gap, are not able to attend. They will be able to make use of these YouTube lectures afterwards also. And second thing which is there, the question answer session, and about that also, if many students would like to get in touch with you, to please guide them also. This is our request. So once again, thank you so much, Dr. Narayan Rao. keep supporting the initiative of the SAMA to spread the knowledge in the South Asia and other developing countries. Thank you.
Thank you.
Thank you. Thank you, Ajay sir. Today's lecture will be delivered by Dr. T.N. Rao sir from NARL. So now I invite Dr. Lakshmi Kumar for introducing the speaker.
Thank you, Dr. Rakesh. And so I'm very happy to introduce Dr. T. Narayan Rao on this occasion. So just points. Dr. T. Narayan Rao received master's degree in physics with distinction from Andhra University, Visakhapatnam. And later, Sir has done MPhil and PhD degrees in the field of atmospheric physics from Sri Venkateswara University, Tirupati. Sir was postdoctoral fellow at Swedish Institute of Space Physics, Kiruna, Sweden during 2002-2002, and he was JSPS fellow at Hydrospheric Atmospheric Research Center, Nagoya, Japan during 2002 to 2004. Since in November 2004, Sir has joined as scientist in NARL, Gadanki, India, and his research interests include dynamics and microphysics of precipitation systems, convection in Asian monsoon, stratosphere-troposphere exchange process in the tropics and extratropics, structure and dynamics of atmosphere boundary layer, radar and GNSS meteorology, and atmospheric turbulence. Dr. Narayan Rao sir has authored and co-authored almost 120 papers in reputed international journals, and main importantly, sir has given, there are 13 candidates have been awarded under Sir's guidance for their PhD. Sir is serving and served as the member and convener in many national committees, and also as a core member. He is a core member in SERB and PAM member in Ministry of Earth Sciences. Presently, Sir is serving as the associate editor for the Journal of Earth Science, Earth System Science, and Journal of Atmospheric and Ocean Technology. Sir is a fellow of the prestigious Indian Academy of Science, Bangalore, and Indian National Academy, New Delhi, and also recipient of ISRO Team Excellence Award and JSPS Fellowship. So with this few words, I welcome once again Dr. T. Narayan Rao sir, so for his talk. Over to you, sir. Thank you.
Thank you, Dr. Lakshmi Kumar sir, for introducing the speaker. So now I invite T.N. Rao sir for the lecture.
Yeah, thank you very much, Lakshmi Kumar, for your kind introduction, and also Tyagi for your introduction. And also, first of all, let me thank Sama for inviting me to deliver this talk. Originally, I'm supposed to deliver another talk, but I thought that because before me there was another talk scheduled, but then that talk was not happened. So without that talk, it is very difficult to understand my talk. So I preponed my second talk to today, and then today's talk I will give a little later, maybe after 2 weeks. So today I'm going to talk about wind profilers for meteorological applications, this is the outline of my presentation. First, I'll talk about some basics of wind profilers, and then what kind of frequency we operate, and then why we operate, how to choose the frequency for a particular application, and what are the targets for wind profilers, what are the relevant scattering mechanisms, then how do you process the data, and then what kind of techniques are available for profiling the wind. Like Doppler beam swinging and then spaced antenna. And then most part of my presentation will talk about the operational applications and then research applications. So if you see a spectrum of meteorological radars, actually we can broadly divide it into 3 categories. One is from 30 to 1.3 gigahertz or something like that. So these are all actually VHF, UHF. These radars operate at VHF frequencies. So we call them as wind profilers. simply, these are also called as a clear air radars, because for these actually during the clear weather also these radars will operate. So we call it as clear air radars. Then you have probably you may be hearing about the SCX band radars, these Doppler weather radars. The last 10 talks. These are all basically the targets are the raindrops. So on through that actually we study the tropical cyclones, severe weather systems, and then we also estimate the precipitation. And then there is another class of radars, very mostly operate at either Ka band or W band. So they are all basically to study the clouds. So there are three classes of meteorological radars. One is a wind profiler, other one is the Doppler weather radars, and then cloud radars. So we can broadly categorize into three categories. So I'll skip some of the slides. If you see the historical development of this wind profilers or MST radars, MST actually stands for mesosphere, stratosphere, troposphere. So originally these wind profiler technology started with MST radar technology, and then wind profiler nowadays the common people commonly call smaller smaller radars as wind profilers, but then it's actually the technology is same for all the MST radars, ST radars or wind profilers. So this technology actually started from 1930s when they have seen these ionospheric people using long wavelength radar. They have seen some echoes from the troposphere. So they know that they used to call it as angel echoes, phantom echoes, ghost echoes, like that. So they know that they're coming from the refractive index fluctuations. Either refractive index fluctuations caused by the turbulence or from the temperature sheets or from the strong thermal inversions. So then later several theories were developed to understand these echoes. And then in 1960s, there are very powerful high frequency, very powerful radars were developed for ionospheric applications. And then there actually from there, this pioneering work from Woodman and Gillen in 1974 using the Hikamarka Peru radar. See that he has actually explained and then he has shown that how to derive wind profiles with this kind of echoes. So then that led to the development of MST type of radars, and this class of radars since then became very powerful radars, and then they dominated the atmospheric radar scene over several decades. So then subsequently the top left, this radar is the Hikamarka radar. This is where actually the technique of MST radar was developed, and since then several radars were developed in different parts of the world. This is the Japanese radar, and then this is the Indian MST radar, which was the second largest radar in the world. And then this is the most powerful radar. Presently, it has renovated and then it became very powerful radar now. And then several radars were developed and then worldwide. Since you have already heard about the Doppler weather radars, I will not going to talk about the hardware part of these radars. So what I will do is I will mostly focus on what are the differences between the weather radar and a clear air radar or a wind profiler, so that you will there is no repetition will be there. So you see that for a weather radar, the basic radar technology is same. Basic radars are same. You have a transmitter, you have a receiver, you have an antenna, and you have a duplexer. The duplexer will connect antenna to the transmitter during transmission, and then during reception it connects to the receiver, and then the processing. So the basic difference is here. For example, you have a different type of antenna you use in weather radars from the wind profilers, and then the targets are different. The basic scattering mechanisms are different, and then processing of the data is different. Except that, then basically the basic configuration will remain same. It remains the same. And then you see here for the weather radars, the precipitation particles, the raindrops and the ice particles are the main targets for the weather radars. Whereas for the clear wind profilers, the refractive index fluctuations are the main targets. So it will be very clearly shown in the next slides. Actually, these For the wind profiler, actually there are two types of scatterings. One we call the clear air scattering, and the other one is the particle scattering. In the clear air scattering, you have three types again: Bragg scattering, Fresnel reflection, and Fresnel scattering. Particle scattering, you have Rayleigh scattering and Mie scattering. So what is the clear air scattering and what is the particle scattering? If you see that, actually the most of the wind profilers get the backscattered echoes mainly from the refractive index fluctuations that are caused by the turbulence. And then if it is entirely by the turbulence, then we call it as the Bragg scatter. And then it is there is a strong inversion or something, temperature inversion exists, then there is a large discontinuity will be there in the refractive index. So the radio wave propagate, you get a very strong backscatter reflection from the such layers. Then you will get the Fresnel reflection. And then within the radar volume, if you have these kind of small layers existing randomly spread, randomly existing this kind of, if randomly they exist, then you will get the Fresnel scattering. So these are the basic three scattering mechanisms that are relevant to the wind profilers. And also some of the wind profilers get echoes from the particles, also rain particles, rain and ice particles. Okay, so basically the basic mechanism is the Rayleigh scattering, and then probably you might have heard about the Rayleigh scattering when the wavelength of the probing radar wave radar is actually very large compared to the particle size. Then you call it as a Rayleigh scattering, whatever scattering you get. And then if they're comparable in size, then you get the Mie scattering. And then there is other difference between this Doppler weather radar and wind profiler is actually the beam steering. Normally the traditional existing Doppler weather radars mostly use servos and then to rotate your antenna. But whereas in the case of wind profiler, we use the phase difference between the different arrays. So that phase difference will tilt the beam because mechanically moving this much big radar is not possible physically. So then what we do is we introduce some phase shift between the arrays. So you will get the beam will be tilted. There another difference is most of the Doppler weather radars normally we do is the scan strategy will be we will point the beam in very close to the ground. So so the 0 degree elevation, 1 degree elevation, 2 degree elevation, like that. That is because the main job of the Doppler weather radar is to measure the precipitation, whereas here the main job is to measure the wind. So that's why we point the beam only close to the vertical. Maybe we will tilt only 10 to 15 degree off vertical in the case of wind profilers. So that is the basic difference between these two in terms of the steering. So the wind profilers operate at different frequencies, and then based on the application, you have to choose the frequency. For example, those who are interested in the mesosphere, stratosphere, troposphere, and ionospheric application, they have to choose a 53 megahertz, around 50 megahertz. Those who are interested in the stratosphere, troposphere, then they have to choose a different type of frequency, around 400 megahertz. Nowadays, 200 megahertz radars are also there. Those who are interested in boundary layer applications, so they have to choose a different frequency. Mostly they choose around 1 gigahertz. So depending on their application, they have to choose their frequency of the radar. So this is the basic criteria, because if the refractive index fluctuations, that's what we call as the target. So the targets, if they have to exist, then the target they exist only in the inertial subrange, because most of these discontinuities are formed in the buoyancy subrange, and then they break down to smaller scales, and then finally they break down to very small scales, and then because of the atmospheric viscosity, they finally convert it into heat energy. So for the radar to work, for this wind profiler to work, then the target should be in the inertial subrange. So the inertial subrange, if you see the vertical structure of the inertial subrange, you see the only 3 meter scale only exist here. 3 meter scale only exists up to the 70-80 kilometer. So that's the reason why we have to choose around 50 megahertz for mesosphere, stratosphere, tropospheric radars, and then if you then for the other high frequency radars for the tropospheric applications. So if you see the processing, because most of the Doppler weather radars, they use pulse pair technique to get the parameters, whereas wind profilers use a different technique. So once from the up to IQ channel, it is same, and then from the IQ channel, once you get, then you do the coherent integration. Then I'll talk about these each separately, but then we will do a coherent integration to build up the signal. And then then we do the Fourier analysis to convert the time series data into the frequency domain, and then again we do some incoherent averaging. Then finally we get the spectra, and then that power spectrum we will process in offline to get the moments, and then finally UW. And then let us see each step in detail. See, for the coherent integration, why we do coherent integration is just to build up the signal, because the atmospheric variations, the wind variations are they occur at different scales, but the smallest scales will be the order in few seconds. But whereas your radar sampling is actually is happening at a much higher rate, so you don't need those many samples to calculate the wind. So what we do is, and then also your backscattered signal is very weak, because your target is actually only the refractive index fluctuations. So it's not a hard target, it's a very soft target. So your backscattered signal is also very weak. So we need to integrate several samples to build the signal. And then also, as I told earlier, then we don't need these many signals to process the to derive the wind profile. So that's why, to reduce the volume also, what we will do is we will do so many coherent integrations, so that we will improve the signal, and also we will reduce the data volume. And then once we integrate the several signals, and then we do Fourier analysis to get the spectra. Once you get the spectrum, then what we do is, actually the spectrum will look like this, with you have a signal and you have a lot of noise here, and then some clutter also can be there in the signal. So, and sometimes your signal will be almost comparable to the noise floor. So in such cases, what we will do is, if you integrate several spectra, then what will happen is all the noise will get add randomly, and then that will be smeared out, whereas the signal will remain at the same time. So what happens is, because of that process, your detectability of the signal will improve. So that is how we do several incoherent integrations to clean your spectrum. So once you get the spectrum, it looks like this. This I have shown it only at one range gate. So you have noise here, and then you have a spectrum. You have a signal here, and then you do you estimate first the noise floor, and then remove the noise floor, and then you identify these valley points, and then from there you integrate your signal here. Then you will get the power zero. That's what we call the total power, the zeroth moment, and the first moment, using this formula, is a power weighted first moment. This first moment is actually the Doppler, and then second moment is the variance. So these three parameters are the basic parameters that you will get with a wind profiler. So the backscattered power, whatever you are getting, that indicates how strong is the signal. And then the Doppler tells you about the velocity of the target, and then the variance tells you about the turbulence, intensity of the turbulence in the atmosphere. So these are the three basic parameters that you get with a wind profiler, and these three parameters we will use it for various applications. So once you get the power spectrum, it will look like this. This is the x-axis. You can see here, I have shown some 5 power spectra. One is actually you can see here, y-axis is the height and x-axis is the Doppler. And then each height, you can see the signal here, it's a Doppler shifted signal. And this is the east beam, this is the west beam, this is the vertical, north and south beam. So the 5 beams I have shown here. And then like this, if you get the velocity, the Doppler velocities, and then from the Doppler velocities you calculate the vertical velocity and the horizontal velocity, and using these formulae, or otherwise also we can calculate directly from this matrix method. So once you calculate the base, the first thing you do is actually you validate the data. So we can show here, we have shown here this, we have validated with the wind with other GPS radio sound derived winds, and you can see most of the points are falling on along the diagonal, so indicating that it is the validation is very good. And here also one case we have shown here, the validation, wind validation of the Indian hemisphere radar. So the technique, whatever I explained till now, is actually is called Doppler beam swinging technique. So what we are doing is actually we are using different, we are pointing the beam in different directions, and then we are getting the radial velocities in the direction, and then from the radial velocity we are deriving the horizontal winds and vertical wind. In the same way, there is another technique called spaced antenna technique. In the spaced antenna technique, the major difference is here we don't point the beam in different directions, but then we receive the beam with the different receivers, spaced receivers, and then we do the cross correlation and then autocorrelation, and from there we retrieve the parameters. But most of the wind profiling radars use this Doppler beam swinging technique for operation, but some wind profilers they use spaced antenna also. But for example, I am showing one example here. This is with our Indian MST radar. Now with the present Indian MST radar, we can operate the radar either in the Doppler beam swinging mode or also in the spaced antenna mode, and then you can see the comparisons are all very good. So the basic, but then people can use any of these techniques to get the wind profiles, either Doppler beam swinging technique or spaced antenna technique. The main advantage of spaced antenna technique is because here we are using only one beam, you will get wind with very high resolution, and also with the Doppler beam swinging technique, basically we have to, if you have to assume that there is a uniform atmosphere between the beams. So the whatever volume it is occupied by different beams, we assume that the atmosphere is uniform, but sometimes that condition may not be satisfied. So in that case, you will get a wrong wind estimate. But whereas since we are using only one beam here, so that assumption is not required in the case of spaced antenna technique. And also you will get some more information about the scatterers with spaced antenna technique. So now if you see the applications, I just categorized the applications into two different categories. So one is the operational applications, the research applications. Operational, we use it for forecasting, then aviation, wind support for rocket launches, air quality meteorology. And then for research, there are so many research, there are so many research applications with wind profilers, starting from the boundary layer process, and then the turbulence, atmospheric waves, atmospheric stability, then convection, precipitation, stratosphere, troposphere exchange. So many processes you can study with wind profilers and MST type of radars. So realizing the potential of wind profilers, several countries have started networking the wind profilers. So in US, they had a NOVA profiler network. So 32 wind profilers operating at 404 megahertz, around 400 megahertz. They were all networked, and then they provide hourly wind profiles to all operational agencies. Similarly, in the Europe also they have several radars. They were networked, and all the data goes to operational agencies for assimilating into their models. Japan, of course, has a different type of wind profiler network. They use a 1.3 gigahertz wind profiler network, and the JMA also uses these wind profilers in their analysis, assimilation and analysis. And this is one paper which I really liked it most, because this talks about, this is actually the cover page of the Bulletin of American Met Society. They have shown that what is the value of wind profiler data in US weather forecasting. And then what they have found is after assimilating this data, they have noticed that there is a reduction in the overall error in short-range weather forecast. So particularly they have seen that there is a lot of improvement in the short-range weather forecast. And then there is a substantial reduction of wind forecast error after assimilating this wind data in the model. And for example, for various aviation applications, actually you see that I told that this radar can measure the atmospheric turbulence, clear air turbulence, and then also and you know that these are the two major aviation hazards. One is the clear air turbulence, another one is the microburst. And you see I have shown here several exam paper cuttings from the newspapers showing that then what severe turbulence can cause to the passengers. So, but then the advantage with the wind profiler is actually directly provides the at a clear air turbulence at different altitudes. So that information will be very useful for aviation purposes. That's why at many airports actually they normally they install some wind profilers not only for the turbulence but also for the for identifying the microbursts. And then you all know that most of the meteorologists know this about the microburst. When these thunderstorms die, then the strong downdraft will they emanate from these thunder clouds. So they will come like and then they will hit the ground and then will go like this. And so the flights actually when they encounter it can cause a devastation. So and then because the advantage with the wind profiler is it provides continuous wind information, particularly the vertical wind information, so we can easily identify this kind of the microbursts with wind profilers. There is another application is actually the rocket launches. This is actually with the Indian MS radar I'm showing here. When the rocket launch is scheduled at a particular time, because they generally launch balloon a few hours before the launch, just to put the to give that to that wind information to the software, so that the rocket will actually come to know that what kind of wind it will encounter during its when it is going up. But then from few hours before to the actual launch time, they don't get that wind information. So radars will provide that information. So what we do with Gadanki is actually we provide continuous wind information to the Sriharikota, so that they will see that what is the wind persistence from the whatever time they fed the data to the software to the actual launch time. So that wind persistence they will see, and if there is a large difference between the whatever they have fed to the software and to the from that time to the launch time, then they have to take a decision. So this is very crucial for rocket launch applications. And then in Sriharikota now they have a wind profiler operating at 50 megahertz. And then this is air quality meteorology. And then the radar is basically provides the two important parameters. One is the wind speed, wind direction, other about the wind information, other one is the turbulence information. For air quality meteorology and for the even the nuclear power plants, and when they release some effluents or some dangerous gases, they wanted to know actually in which direction these gases will travel and how quickly they mix with the background wind. So what they need is actually the wind direction information, wind speed and direction information, and also that turbulence information. Speed and direction information to know that in which direction these gases will go, and then the turbulence information just to know that actually how quickly it will mixes with the background air. And then these wind profilers will provide both the wind speed and both speed and direction, and also the turbulence information. So it will be very useful for air quality meteorology for particularly these nuclear power plants and other things. And that as I told you that there are various research applications are there for wind profilers, starting from the boundary layer to the turbulence to the stratosphere troposphere exchange, and then for clouds and precipitation for meteorological applications. And apart from all these meteorology, the tropospheric application, there are other applications. The MST type of radars are extensively used to understand the mesospheric dynamics. Then particularly the mesospheric inversion layers, then also the ionospheric irregularities like E-region irregularities, and then quasi-periodic echoes, 150 kilometers echoes, and then spread up, and several other processes. But today I'm going to focus mostly only in the lower atmosphere and meteorological applications. So I will cover only the bottom three applications. So what is the main advantage of a wind profiler? If you see this, it provides continuous information, continuous wind profiles, and continuous information of turbulence. The major advantage of any wind profiler and MST type of radar is actually they provide continuous information. So you will understand the atmosphere in much greater detail. And then suppose if you launch a balloon, then you will get a wind profile, but then that is relevant, that is only applicable only at that time. Particularly if you see a profile, a wind variation like this, you can see here, this is during the passage of a cyclone, and then you see the wind variability within 2 days. And then if you launch a balloon, and then it hardly covers this kind of variability. So that is the major advantage of this kind of radars. You provide, you get the continuous information, so you can see the variability of the atmosphere in a greater detail. So, and then if any diurnal biases are there, then that also you can correct with wind profilers. Then as I told you, that in the atmospheric boundary layer, because most of the atmospheric variability, variability is very large in the atmospheric boundary layer. So that kind of variability also you can get with this kind of wind profilers. Then measurement of clear air turbulence, because Doppler weather radar operates only when you have a cloud or precipitation. Of course, as band radars, we do get some echoes from the clear air from the backscattering, but then most of the other radars, they don't get any backscattered echo. So they are all mostly depending on the Rayleigh scattering. So when you have a cloud or rain, then only you will get echoes. But whereas these radars will continuously, they operate during the clear weather also, so you get the information about the clear air turbulence. And then these radars are also are extensively used to study the stratosphere troposphere exchange process. And also the uniqueness of this radar is actually it provides the vertical wind, because radio sounds will provide horizontal winds, but they don't provide the vertical wind. So the uniqueness of this radar is basically it provides the vertical wind. So the vertical wind is the you can use the vertical wind information, because vertical wind is very crucial for convection and other atmospheric processes, and also the stratosphere troposphere exchange motion. So this advantage we can use for several applications. So for example, you can validate the model performance, how well the model is able to reproduce the observed vertical wind with MST radar. And then also MST radar vertical winds also can be assimilated into the model, and then to improve the this kind of disturbed weather conditions. Actually some of the radars actually get echoes from the background air through backscattering, and also information about they provide information about precipitation through Rayleigh scattering. In such a case, you can also derive the drop size distribution. So raindrop size distribution will provide they will give clues about the what kind of microphysical processes are occurring inside the clouds. So then we will see one example of each of these things. See the continuous profiling of winds. You can see here, there is a large variability here in a wind within 3 kilometer, and then you see the low level jet normally it peaks in the early morning time here at 5 o'clock, whereas if you use a balloon in the evening, then you will completely underestimate the strength of the low level jet as well as the height of the low level jet also. You'll estimate wrongly. So because the wind profilers provide such continuous information, so you will come to know the at what time actually the wind peaks, and then what is the actual strength of the low level jet here in this case, and then what is the actual height of the low level jet. So this kind of information is possible. So this kind of diurnal biases, if any, if you are having only one measurement or two measurement in a day, those things also we can correct with the wind profilers. And then, as I said, that since it is possible to get the continuous information with the wind profiler, so you can see here actually the how the boundary layer is evolving here. See, we can get the boundary layer height with a wind profiler, because the near the top of the boundary layer normally you get a very strong backscatter. Because of the discontinuity in the refractive index, then you get a very strong backscatter at the top of the boundary layer. So from there you can identify the top of the boundary layer, what is the boundary layer height, and then you can see that once you know the height of the boundary layer, and we can study the how the boundary layer is evolving in a day. Okay, so and then you can see that the strong thermals within the boundary layer here, and then so the several atmospheric boundary layer processes you can study with the wind profilers. There are so many studies with wind profilers, and then you can also calculate, for example, if you are interested in the air pollution, then you can study the ventilation. We can directly calculate the ventilation coefficient, and then how it is varying in different seasons. All those things you can study with wind profilers. And this is another study that we have conducted here. We can see the boundary layer, how it is changing in dry spell and wet spells. And then you see in the dry spell, the boundary layer evolution goes up. Boundary layer actually evolution is very clear here. And then also boundary layer goes up to 2-3 kilometers here in this panel. And then during the wet spell, actually the boundary layer goes only up to 1.5 kilometer. This is what we expect actually, but then what is not known is actually during the wet spells, it is not only the height of the boundary layer is shallow, but also the evolution of the boundary layer is also delayed by 1 or 2 hours. So because since we have the continuous observations, so we are able to see this kind of evolution, and then you see the differences in dry and wet spells and how the evolution has changed based on the soil conditions. So as we expected, actually, in the boundary layer, during the dry spell, you don't have the soil moisture is very low here, so all the net radiation gets converted into, most of the net radiation is getting converted into the sensible heat flux, and then that dries the boundary layer to very high altitude. And then whereas in the wet spell, most of you have a lot of soil moisture on the ground, and then most of the net radiation is getting partitioned into latent heat flux, and then and then the sensible heat flux the component is very low, and then also that delays actually the total the evolution of the boundary layer in the wet spells. Not only you see a shallow boundary layer, but also the evolution also started a little late in case of wet spell during wet spells. This is another very interesting process that we have seen with wind profilers. Normally, the atmospheric atmospheric boundary layer is very turbulent during the daytime. During the night time, it becomes highly stable. That is what we know, and then theory says. But then we see that actually on many days we see very strong turbulence after the sunset. So this is mainly is happening here. So what is happening is, what we expect is everything settles down, all pollutions and everything will settle down during the night time, but then again this turbulence engine starts. So this is the kind of a unusual phenomena that we are seeing here. So that tells actually this our understanding about the boundary layer is also not complete, because these kind of things this happening after the sunset. Generally after the sunset also, these sometimes we see turbulence very episodic manner, when you have a strong shear or some wind shear or something. So episodic turbulence normally people have seen earlier, but here it is almost like nearly 70% of the days we see this kind of thing, very intense turbulence after the sunset. But and then the intense turbulence, the intensity of the turbulence is almost comparable to the daytime. Sometimes it is larger than the daytime turbulence. So such kind of interesting atmospheric phenomena phenomena were actually seen by seen by the wind profilers, and because of this continuous observations. And you know the importance of the atmospheric turbulence, so I'm not spending much time on this. Actually, how a turbulence, how we can study a turbulence with wind profiler. See, for example, if the wind is blowing in this direction, and then this is your radar beam, and then there are so many
Weapon, is everything okay?
I think there is problem with this network.
I mean, from the speaker side?
Yes, sir.
Okay. Can somebody call Dr. Narayana? Mr. Rakesh, you have his phone number?
Sir, I will call. I will. Sir, is there a problem with your network? Hello? അവിടെ പിള്ളേരെ ഫുൾ ഔട്ടാന്ന് തോന്നുന്നു.
Disconnected. We have the virtual hazards, online programs. So, Mr. Salam, how is the situation in Dhaka? Can you hear me?
Yes, sir, I hear you and I am still here. And last few days, we are in a bad situation. I think all of you know the present situation of Bangladesh. Last
the office open? No, BM is open?
Yes, office is open. Every operational activities is going on.
Okay. But airport is still closed, right?
Yes, some violence is occurred in airport. So some terrorist, some person try to leave Bangladesh.
Okay.
So the authority closed the airport.
Now Dr. Now is back. So yeah. So we can talk later, okay?
Okay, thank you.
Yes, yeah, we can hear you, sir.
Okay. Okay, I think it got disconnected here.
Yeah.
Okay, so don't worry about so many figures here. But then, what is important is actually the the observed spectral width, whatever sigma square observed, is actually a combination of several things. So these non-turbulent contributions like beam broadening and shear broadening and then wave broadening, these things can be removed, and then directly we can observed spectral width like sigma square observed, we can from there we can calculate once after removing these non-turbulent contributions, we can calculate the sigma square turbulence. So directly we can calculate this the turbulence intensity at different heights. So that is the main advantage of this wind profiler. So you get at different altitudes the clear air turbulence, and continuously you will get this information. So there's another important aspect is because some time back I said that there are three scattering mechanisms that are relevant for these MST radars. Is actually one Bragg scattering, Fresnel reflection, Fresnel scattering. So Fresnel reflection mainly occurs when you have a very strong temperature gradients, like temperature inversions, and then whenever you have some temperature inversions or anything like that. So the bigger one of the temperature inversion is the tropopause, where you see a temperature instead of decreasing, it increases from there. So we can identify the tropopause altitude, and also if any there is a temperature inversion at a lower altitudes, also we can identify uh, mainly from the by checking the backscattered powers of vertical versus off vertical beams. So vertical beam normally you get a very strong backscatter because it's a you're getting a reflection from from the refractance fluctuation gradients. Whereas with off vertical, if you use a off vertical beam, the reflection goes somewhere else, not to the not it will not come towards the antenna. So you will get a weak backscatter when you're using off vertical beam, whereas if you're using a vertical beam, you will get a very strong backscatter. So by looking at the backscatters of vertical and off vertical beams, we can also identify the atmospheric stable layers, and then all like tropopause and other stable layers. So this is actually one event I'm showing. This in atmosphere, you have so many waves of different period. You have waves of different periodicities and then different amplitudes. So one of the most important atmospheric wave is the atmospheric gravity wave, which is very important for this from circulation point of view. See, so one of the sources in the particularly in the tropics, the main source is the convection. And I'm showing one example here. So you see a very strong convection here where the vertical velocity, this is the vertical velocity. Vertical velocities actually are exceeding 5-6 meter per second here. And so that the convection actually is triggering. It is actually the stable atmosphere. It is actually destabilizing and then creating the gravity waves. So you can see here on the top portion of the graph, you see so many waves here, the up and downward motions here. So they are all atmospheric gravity waves triggered by this intense convection. So these kind of atmospheric waves we can study by what are the characteristics of this kind of atmospheric gravity waves, and then what is how they propagate into the atmosphere, and then how much momentum flux they deposit, how much momentum they deposit, and how much energy they carry to the higher heights. All these things we can study with this kind of MST type of radars. Uh, so and I think most of you are very familiar with these processes, the stratosphere troposphere exchange processes. In the tropics, it is mostly the exchange occurs from the troposphere to the stratosphere, whereas at high latitudes it is actually the other way. The exchange, most of the exchange occurs from the stratosphere to the troposphere, so it's a big circulation. And then most of the exchange occurs through intense convection in the tropics. And then there are several theories people have proposed. They thought that actually most of this exchange is happening in two regions. One is the India during the monsoon time. Other one is the Indonesian sector. These are the two convectively active regions. So the most of the exchange is happening in these two regions. They call it as these two regions are called stratospheric fountain regions. And then there are so many theories were developed around that. And then fortunately we have two such wind profilers. One wind profiler is at Gadanki and one wind profiler is at Kotata Bank, similar kind of wind profilers, MST type of radars. So we used, actually we wanted to see whether really the stratospheric fountain hypothesis is correct or not. So what we did is we have checked these things. We have taken some 10 years of data here, and then we have averaged all 10 years of data to see the what is the vertical wind, how the vertical wind looks like if you average for 10 years. So when we saw that, actually what we found is at both Gadanki and Kotata Bank, actually the wind is actually not going, we don't see any updraft from ground to the up to the stratospheric altitudes. And we see mostly in the lower region, below 10 kilometers or so, we see the downward motion, whereas above it you see an upward motion there. So then we proposed that this transport is not happening the continuous from ground to the top. It is actually, it is a two-step process. In deep convection, in convection it is going up to some height, and then most of the convection generally goes up to 10-12 kilometers. So the convection is taking up to 10-12 kilometer, and then slowly it is ascending. From then onwards it is slowly ascending into the stratosphere. So it's a two-step process. So these kind of theories we can actually we can evaluate, and then also we can propose a new type of theories with this kind of wind profilers. And also when you have a penetrative convection, that when the convection goes even penetrating that the tropopause, it goes into the stratosphere, then we can see that what kind of exchange is happening. But once you calculate the turbulence there, then we can see that the turbulence is the one which is irreversibly exchanging the air within the convective cloud into the outside into the stratosphere. So, and then we have studied that actually what kind of these convective core, when the convection overshoots the tropopause, then what kind of when you have updraft convection, updraft course and downdraft course, and then how the intensity of the turbulence is changing in up and downdraft course. And then it is very clear that actually in convective course the turbulence intensity is nearly 4 times larger than in the normal air, in the clear air. So the intensity of the turbulence increases drastically, but in convective course. So it is nearly 4 to 5 times. Sometimes we have seen an order of magnitude difference in convective course compared to the clear weather, fair weather conditions at the same altitudes. When you talk about the when I also said that actually this MST type of radars, um, they get echoes from both clear air and precipitation, and then some high frequency radars, wind profilers, will get echoes only from the Rayleigh scatter. So that's mainly because of it's a frequency dependence. With frequency dependence, it depends on the frequency. For example, Rayleigh scattering dependence, I think you are all familiar with this by now. This actually it is a 1 by lambda power 4. So if the lambda decreases, then you get a strong Rayleigh backscatter. Whereas the Bragg scattering, which is which is relevant for the most of the wind profilers. So the dependence on lambda is weak compared to the Rayleigh scattering. That's why you see that the wavelength changes. The Bragg scatter doesn't change much, whereas the Rayleigh scatter changes drastically here. So because of that, if you use a VHF wind profiler, you get echoes from the Bragg scatter as well as the Rayleigh scatter. Whereas if UHF profiler, you will not see the Bragg scattered component when you are using a UHF profiler. You will get only echoes from the rain particles. There is a Rayleigh scattering only you will get here. Uh, so that the dependency also you can see, and using this potential, if you have both radars together, then you can derive several parameters, several microphysical parameters, particularly with when you have these two echoes. Okay, so that is the advantage of this wind profiler, that we will see little later, and how we are utilizing this the capability of this wind profiler to get the microphysical parameters. But when you have these two echoes, you have other problem also. Then how do you identify which one is what? Which one is clear air echo and which one is the precipitation echo? And the other thing is, how do we how do you estimate moments for clear air echoes and also for the precipitation echoes? So now we have several algorithms were developed to automatically identify and calculate the moments for these both clear air echoes and precipitation echoes. So once you have these the moments for the precipitation echo, for the clear air echo, the backscattered power tells you about the intensity of the the target. Here also the backscattered power tells you about for the Rayleigh scattering, also for the precipitation, also precipitation backscatter, also you will get the backscattered power indicates the particle the precipitation intensity. So if you can calibrate your radar, calibrate, if you can backscatter power, if you can use it to calibrate the radar, then you can directly calculate. That means you are getting a reflectivity, so you can directly calculate the rain rate from the Jada relations here also, just like a Doppler weather radar. And also we can use backscattered power to classify the precipitation, also different types of precipitating systems also we can classify. And then the power weighted mean Doppler velocity in the case of a clear air, then it tells you about the wind velocity. If the wind is coming towards you or going away from you, what intensity, and all this information you will get from the Doppler velocity, mean radial velocity. In the case of Doppler, in the case of the precipitation echo, it tells you about the fall velocity of the hydrometeor. Okay, so you will get that information also directly with the wind profiler. And then in the case of a clear air echo, the spectral width gives the indication, which gives information about the atmospheric turbulence. Whereas for a precipitation echo, it gives information about turbulence, as well as it also gives the information about the raindrop size distribution. So here is one example I am showing, that once you have this information, for example, the top panel figure shows that the vertical wind during a convective system, and then you can see the wind vertical winds going up, the vertical winds are of the order of 5 to 6 meter per second here most of the time, and then up to 16-17 kilometer you see such a strong updrafts. So these kind of profiles we can use, this kind of the range height, the time height velocity maps we can use to study the characteristics of convective draft course. And then you can see sometimes you see the downdrafts also, sometimes you see updrafts also. So we can also study the what is the convective updraft, what is the strength of the convective updraft, and what is the strength of the convective downdrafts, and all those things. And then we can also study that whether these drafts are how these drafts are varying, how the draft strengths are varying in shallow, deep, and decaying convections. Okay, so all these characterization of convection we can do with wind profilers. And here is one example I am showing. During the active monsoon spell and during the break monsoon spell, the characteristics of convective draft course are completely different. In the convective, in active monsoon spell, you see very strong updraft in the upper troposphere. This is a mean profile, not a one profile. This is the convective. This is a mean profile. Whereas in the break monsoon spell, you see a different type of, is a bimodal structure. You see bimodal convective draft core. You can see in the break monsoon spell, and there are differences. Actually, you see these kind of differences, and then you can also study why these differences are coming, and what could be the reason for these differences. And then here also you can see what the extent of the draft course are completely different in active and break monsoon spells. So these kind of things we can study with wind profiler. And then also we have seen that actually the orientation of the draft core, like this, the orientation, also the shape of the draft core is also different in these spells. So why these kind of differences are coming, all these things we can study with wind profilers. As I said before, uh, this is the only instrument probably provides the vertical wind information very accurately and then very continuously and with very high resolution. So when Dr. Rajivan sir was here, so we conducted an experiment and then we tested different parameterization schemes, and then we have gone with the explicit convection, the cumulus. we have seen the different parameterization, as well as we have also gone to very high resolution so that convection can be explicitly modeled. So even none of these parameterization scheme, and also even with explicit also, we could not get the actual magnitude of the vertical velocity. Okay, so and then even with there is still, we found that there is an order of magnitude difference between the models and as well as in the actual observations. Even if you degrade the resolution of the radar to match to this, still we were not able to get that kind of vertical winds with models. So there is a large difference is existing, so we need to work out why the models are not able to reproduce such large vertical velocity that what we see with radars. And you all know that there are several microphysical processes occurs in clouds and precipitation, when particularly when from the drop nucleation to the drop growth, and then from drop growth, when the drop descends to the ground, also several processes are occurring here. So once you know, once if you calculate at least the drop size distribution below the melting level, so you will able to identify by looking at the variation of the drop sizes. Then you can actually guess what kind of microphysical processes are occurring below the melting layer. Okay, so then the main advantage of this kind of radar is actually, since it is getting echoes from the background, the through Bragg, it getting two echoes, one through Bragg scattering, other through Rayleigh scattering. So using this information, we can also calculate the raindrop size distribution. And it's not only at one height, you can get the profile of drop size distribution. For example, on the right side figure, you can see here these are all these vertical lines are different drop sizes, and then you can see here how the number density of the drops are decreasing as it comes down. Okay, all size drops are decreasing, but only the change in the drop count is actually different for different drop sizes, but they are decreasing. So that is mainly because of this strong evaporation, particularly in the southwest monsoon, this being a summer monsoon here. So you see a lot of evaporation occurs below the below melting layer here. So these kind of several microphysical processes we can infer from the vertical variation of the raindrop size distribution, because under this variation we can also get the continuous the information of the drop size distribution. So we will come to know what is happening, what microphysics process is happening inside the cloud and below the cloud. And you see from in Australia, Sifili and his group, actually what they did is they have derived the drop size distribution, and then they saw that several such events they have gathered, and then they calculated the ZR relation. Once you know the you have the drop size distribution, you can calculate Z and R. So, and from there they have derived empirically these relations, and at different heights, and how they have shown how the coefficient and then exponents are changing as a function of height. So generally with the Doppler weather radars, we use ZR relation to calculate the rainfall rate from the reflectivity using some relation. But that relation itself is not, anyway, we know that the relation is not unique, but then it is also showing here that it is varying with height also. So this kind of information is not known earlier, but now with this wind profilers, I think we were able to get the vertical profiles of the ZR relation and other things. So earlier we had only Indian MST radar was there, but now such radars are there. 5 such radars came into the country, and then we recently started one cooperative research program using all ST-MST radars in the country. So 5 such radars were virtually networked, and then we tried to operate all 5 for a common cause, to study the large scale process. And then we have conducted some experiments, and then we got some results. And then I also if anyone is interested, then they can also join in this program, and then they can also contribute to this program. Thank you.
Thank you, sir. Thank you, T. and Rao sir, for the interesting lecture in wind profilers and its application in meteorology. So now now we have a photo session. So can you request all to switch on the camera? Switch it. എടുക്കൂടാ. Okay, we will take now.
Myanmar, Dr. Calvin, are you able to hear us? Okay. Yeah, please, switch on your camera, please. Yes.
Now I will take.
Yeah, photo system.
Yes, sir. It's okay.
Thank you.
So now it's the time for Q&A section. So I request Millie Madam to handle the Q&A session.
Yeah, thank you, sir. There are questions. I'm starting with the first one. What is the spectral width and what is its importance?
Yeah, the spectral width. As I actually there are two things. One is actually the spectral width coming from the clear air. Okay, so that I told you that this is actually directly tells you about the. Hello.
Yeah. Yes, sir.
Hello?
You can continue. Yes, sir. You can continue, sir.
Yes. The spectral width gives direct information about the atmospheric turbulence. Okay, so as I said, if you have a narrow spectral width, that indicates that the atmosphere is highly stable, and then if you have a broader spectral width, then you can say that its atmosphere is turbulent. So it directly the spectral width links to the atmospheric turbulence, but particularly for the clear air echo. For the precipitation echo, it also tells you about the drop size distribution, the raindrop size distribution. So for the clear air echo, it is turbulence, and for the precipitation echo, it's turbulence plus drop size distribution.
Thank you, sir. The second question is how to do a spectral width correction. Means, is there any way to do corrections?
Yeah, like I said that there are different ways you can correct for spectral width. You can correct spectral width. The spectral broadening is mainly due to the beam broadening and shear broadening. Wave broadening we can neglect because we are only probing for a very less time, so we can neglect wave broadening. But then beam broadening, shear broadening, there are formulas to correct, and then we have tested these formulas because we have the we can change the antenna size so that we can change the beam width and other things. So we tested different beam width configurations, and then after correcting, we found that all actually the all profiles were very consistent. So that indicates that these formulations are correct, and then we can use these formulations to correct for other beam broadening and shear broadening, and so you can get the corrected spectral width, and that spectral width is due to the turbulence.
Okay, sir. Thank you. And one participant is asking and requesting to share an example of STE.
The stratosphere troposphere exchange processes, there are various processes are occurring are there for so one, I told you that actually people thought that all the air is going into from the troposphere to the stratosphere through these two regions. Then later they corrected that statement, and then now there is another hypothesis has come. It's called cold trap hypothesis. That the hypothesis is completely different from the earlier hypothesis like stratospheric fountain. Okay, so that is one example that I have shown, and there are other examples from the stratosphere to the troposphere exchange also, because the tropopause, which is actually folds in a particular atmospheric condition, and then the stratospheric air comes into the troposphere. So that is another example for the exchange between the troposphere and the stratosphere. Another example is actually the penetrative convection, particularly in the tropics. Sometimes the convection can be very deep, and then it goes into the stratosphere and then directly dumps all this material into the stratosphere.
Yes, sir. Thank you, sir. The next question is, can wind profiler measure height of boundary layer?
Yeah, wind profiler is basically gets echo from the refractive index fluctuations, and then near the top of the boundary layer you see a strong gradient, because within the boundary layer you will have a lot of mixing happens, and then above that you have free troposphere. Suddenly there is a temperature, there is a drop in the humidity and then other parameters. So you can expect a strong gradient in the refractive index. So and then you will get a very strong backscatter from the if you're using a radar, you will get a very strong backscatter. So from the backscatter we can identify the boundary layer height, and also we can also use the spectral width variance of the wind variance we can use, or the spectral width we can use to identify the boundary layer height. So there are various ways are there to identify the boundary layer height with wind profiler.
Thank you, sir.
Either
The
with
next,
either with backscattered power or with spectral width we can identify.
thank you, sir. The next question is, how can distinguish turbulence and non-turbulence atmosphere?
There is, as such, there is no non-turbulent atmosphere, but only the turbulence is weak and strong only will be there. So if that's what I told, that if your spectral width is very large, then you can say that it's a turbulent atmosphere. Otherwise it is weak. If it is narrow, then we can say it is a turbulence is less.
Okay. The next question is, sir, a Jada relationship is dynamic. For optimum result, what height or level should ideally be taken in the Indian scenario in summer season?
I think this is a wrong. They should have asked this in the Doppler weather radar community, but then it is as close as possible to the ground. That only I can tell.
Okay. Next question, sir. Yeah. Now there is no question from this Zoom, and just I'm checking YouTube. There is no question in YouTube as well, sir. Okay, now thank you, sir. Thanks a lot for answering the questions.
Okay, thank
Over to
you,
you,
Dr.
sir. Yeah.
Okay, thank you, Millie Madam, for conducting the Q&A session. Sir, now it's over. Sir, Swamishar, sir, can you speak some words?
Okay, well, thank you very much, Dr. Narayana Rao, for very interesting lecture. And you have spoken it in such a simple way, very complicated subject of wind profiler. As you have already highlighted, different applications of wind profiler, especially for the meteorological purposes. Many of you, the participants, they may be aware that from the model, we can retrieve many atmospheric parameters, especially the convective parameters like updraft and the downdraft, etc. They are all model derived products, and we do not know what is the reality or real values for that. So those things can be verified from the observations of the wind profiler. Further, wind profilers can also replace in some way the radio sound, although radio sounds not only provides the wind profile on the vertical, but also provides the moisture humidity profiles. But then in combination with radiometer and the wind profiler, we can get the complete profile of the atmospheric moisture as well as the wind. So in some sense, wind profiler can replace sometimes the radio sounds, because radio sounds are quite costly. For every launch, we have to spend money, whereas in wind profiler, it is a one-time expenditure. Once you have set up it, then you can take the observations anytime you want it. And also, of course, very complex field. You have different kinds of wind profilers like boundary layer or mid-tropospheric, upper tropospheric, and he has already talked about the MST, the radar for the tropospheric, stratospheric wind profiler. So there are a lot of things which are very, very interesting for meteorologists to know, and just one lecture definitely is not sufficient for that. I know he has got one more lecture, but then the topic is different for that second lecture. But I do not know, I mean, whether if Dr. Tian Rao Saab has some time, then he can give some more lecture, one or two more lectures, so that it will completely cover the subject, like even the dual polarimetric radar, for example, which we missed last time. I don't know whether we can request Dr. Anandan again to deliver lecture, but if not, because your first lecture was related to the dual polarimetric radar retrieval of the microphysical parameters. So before that, some background will be necessary to have a talk on the dual polarimetric radars. So all those things are quite interesting and very, very important. I hope that the participants must have benefited a lot. If you have not understood everything in one go or in one lecture, please go through the YouTube recorded lecture and twice, thrice, or as many times as you want. And certainly you will find it very, very interesting, very, very useful. So thank you very much once again, for a very, very interesting lecture. Thank you.
Thank you, sir.
Thank you.
Aditya sir. Aditya sir.
I just wanted to say one thing. Actually, when the wind profilers started, when we started taking the observations during convection, when we found that nearly 15 meter per second, 20 meter per second vertical wind, we got actually very difficult to believe such because we never saw that kind of velocities in the literature. I mean, it is a meteorologists believe that 1 or 2 meter per second in convection or something like that. But when we saw that 15 meter per second vertical wind, 20 meter per second, and I have seen 22 meter per second vertical wind in one case. So they actually completely revolutionized our thinking, particularly meteorologists thinking, particularly from the vertical wind point of view. So that is the first time that we have seen that, and finally when we saw that continuously we are getting such kind of information like 10 meter, 15 meter per second, then we started believing that okay, this is real, this is not a kind of the absolute value. And then regarding my other presentation, um, I will try to include first the, I don't know whether polarimetric, anyone has talked about polarimetric radar.
Not yet. Not yet. Actually, Dr. Anand was supposed to talk, but his talk could not happen last week. So it will be fine. I mean, if you can talk on the polarimetric radar also in one of the lectures, which you can try to schedule. We shall see how it is.
No, that's why I'm asking. Actually, if they don't know anything about polarimetric radar, and if I start about the microphysics and then classification, then it's a little difficult for them to understand. Even now, because some of the basic slides are not there with me today, so I just presented whatever from the conferences. What I presented, some slides I just kept here. But
what we can do is possible, because now all the Saturdays are booked again for the other lectures. So if you have time, then you can fix your lecture on one of the weekdays if possible.
No problem. But no, I just wanted to know, because I have one more lecture.
Yeah.
So that during that lecture, at that time, I will talk about these polarimetric radars and application with the polarimetric radars, and particularly the microphysics, and then hydrometric classification. I will talk about that.
But then in one of your lectures, you are also supposed to talk about the space-based radar.
Yeah, actually, there I'm supposed to talk about phased array radars and space-based radars, spaceborne radars. Phased array radars, anyway, now the wind profilers are all phased array radars only. So maybe spaceborne radars, if you want me to talk, then I will talk separately. But I will talk about the wind profile, these polarimetric radars and microphysics in my next class.
That'll be fine. And that'll be fine. And if required, if possible, we can have a talk on one of the weekdays, because if the Saturdays are all full, then probably possible we can fix on the weekdays, so that we can talk it more elaborately in that case. So thank you so much.
Yeah.
Thank you, sir. Aditya sir, can you speak some words?
Thank you. Very informative, insightful lecture covering applications of the wind profiler in meteorological applications, right from boundary layer to the stratosphere. And the examples which you have given about the diurnal variation, many other aspects of the vertical profile is really very, very useful and illustrative of the power of wind profilers. So thank you so much. I think you have summed up. There is an Hindi saying "Gagar mein Sagar," so you have tried to put in one lecture entire wind profiler applications, right? And that's why probably Professor Someshwar Das wants you to give one more lecture. So, but then I'm sure the YouTube will be of great help to many of us who want to really go through and try to understand little more about the wind profile applications. Thank you so much.
Thank you, sir. Now I invite Dr. Madan Sikal for the vote of thanks.
Thank you for this opportunity. First of all, I like to thank today's presenter, Dr. T.N. Rao, scientist from NARL, for his insightful presentation. And the lecture went very well. I think the participants also were able to learn more things from him. Similarly, I like to thank Secretary of SAMA, Professor Someshwar Das, and President of SAMA, Dr. Ajit Tyagi, for their remarks. Furthermore, I like to thank today's session moderator, Dr. Mili Ghosh from BIT Mesra, for her continuous support. And I like to thank Dr. Lakshmi Kumar for presenting our scientist, Dr. T.N. Rao, today. And finally, I like to thank the session moderator, Dr. Avilas, for this for his time and good, nice presenting the works. And at final, I like to thank all the participants for their time to learn from our guest, Dr. T.N. Rao. Thank you all.
Thank you, sir.
Let me say, Abhilash couldn't moderate today's session because of his some commitment. So thanks to Rakesh for managing it very well. It shows the strength of our team. That yes, similarly I think today our vote of thanks by Madan also. He agreed to deliver that important aspect. So thank you, Madan. Thank you, Rakesh, for managing the show.
Thank you, sir. Thank you. Okay. So now we'll wind up the session.
Yeah. Okay.
Thank you all. Thank you all, sir.
Thank you.